Hi, this is Eli Telovich of the DWR Delta Modeling section. Welcome back to the Bay Delta Schism User Guides. This presentation is part of a unit on gridding, and a common question that comes up in training sessions is how to do mesh refinement in Aquavio SMS. I'll be covering that and assuming you've gone over the introductory tutorials on SMS already, so this might be a little bit fast-moving as a first course. So in this tutorial, we're going to cover global and local mesh refinement, or doubling of the mesh, the need for which comes up both in testing and in near-field studies. We're also going to talk about transitions in channel and open water resolution, which is a subject that comes up in day-to-day gridding, and we'll cover a number of tricks. We're going to talk a little bit about the numerical consequences of refining the mesh, particularly over large regions. And one thing that we're not going to cover is size functions for mesh generation, as we don't use them much. And it's hard to find a size function that catches all the special cases in channelized regions. I think you can find something on Aquavio's website on that topic. If you're refining globally, say as part of a convergence study, the instructions are pretty simple. You just go to the element selection tool on the mesh menu, press Control A or use the lasso tool to select all the elements, right click and choose Refine on the menu as shown on this slide. It takes a while, and you'll want to make sure to check out our checklist on the online topical guide about what to look out for when you alter the mesh. Things like making sure that the locations of hydraulic structures are still in the right place. But conceptually, this is a really easy thing to do. When you are refining on a subdomain using mesh doubling, you do a lot of the same things, but we need to make make a selection. So for that, typically we use the polygon selection method. So I've already created this select refine 111 coverage. I did that by going to map data and new coverage, and I chose area property. So now I go here, go to the select feature polygon tool, press Control A, and then I use the Feature Objects Select Intersecting Objects tool. I choose Mesh Elements on the target grid. And now we will have selected all the elements inside of that grid. I'm going to press Refine. And all of the elements will be doubled. And typically now the issue is going to be at the interface. Okay, you can see here that our approach is a little bit rough. We would like to make a smoother transition. So that's what we're going to look at next in another channel. We're going to look at a way of making this telescope a little bit more from the doubled resolution down to the half resolution. And we're going to do that in a much smaller and simpler place in the domain. Okay, here we are in a somewhat under-resolved section of the Bay Delta mesh. A little bit arbitrary, but it's a nice small section for demonstration purposes. I'm going to go and select a polygon, choose Select Intersecting Objects, Mesh, Elements, and here we have selected the elements. And again, if we go and just do a simple refine, we're going to have a lot of edge effects where the resolution comes together. There's too many elements coming together in a point here. This will behave poorly. Okay, this is a second shot at it, and this time we're going to try and control the transition a little bit. So I've done a few things off screen. First of all, I have drawn in this was the original node. This is kind of a new one. So the idea of this one here, I have made have the same spacing as the one that's going to be upstream in the refined zone. And then immediately downstream, 1/2 of a dx away, I've created one. So this is 5 segments wide. I created one that has 8. So this one's going to double because it's inside of the polygon, and this one it is not. So we're going to have a transition down from 10 to 8, and that's going to work pretty well. Okay, so the next thing that we have to do, oh, and I'm going to also zoom out a little bit. I also drew in the extent of my transition is going to be about 6 or 7 elements, and I've drawn in another cross section. This one is 6 wide. And you can see that sort of the original ambient was 4 wide. So we're transitioning very slowly. If you recall, in the original refinement, they all went away right at this interface, and that's going to be too much of an abrupt transition. So the next thing that we have to do is take care of the upstream to downstream direction. So another thing that you can notice that I've done is in the display options, for annotations and ID, I've enabled the arc directions and the arc ID numbers. And these are essential for, let me show the annotations part because we don't cover that too often. That is here. So what I want to do is ease the transition from what is going to be half of 30, so from about 15 back to about 35 downstream. So what I'm going to do is I am going to, I know what direction the arrow is going, and so I can use the redistribute min-max spacing option and go from, let's say, 17 to 33 sounds about right. I'll use the cubic spline, and voila, we've got something. This is maybe a little bit wider than that. That's pretty good. And now we'll have to reflect that over from onto arc 23. So I'm going to do redistribute source arc onto 23. Okay. This is going to ease the transition a lot. Oh, by the way, I think I already said when you do min-max, the min has to be on the up arrow side, and the max has to be on the down arrow side. And if that means if you need to flip things, you can always go reverse art direction. Okay, so now let's build up the local part of the mesh. Okay, and I'm gonna go to the refine selections and select intersecting mesh elements, and I'm going to refine them. So this is the same steps that we've been taking before. Okay, then one last step. We've only been concerned with the downstream. You can see that this is still kind of crazy here. You can select the triangles and merge triangles, and you can make selections to do this as well. We do track merge selections. So you can see that now you get a pretty nice transition from upstream to downstream. I mean, most of the issues here just have to do with the original mesh having been a little bit crude, but the transition is pretty nice. And if we had adjusted these vertices even a little bit better, it would have turned out even nicer. That's the automatic way to do things. I want to also acknowledge that sometimes people get gridding fatigue and they do a lot of that last step by manually. So you can do that by just putting a vertex halfway moving the second to about halfway between here and here, you can take that as far as you want. It's easiest to do if you only do the transition in a very finite amount of space. So it's not going to be as nice, but we can watch and see how it turns out. That moving it to halfway part is important. It's nice to have a marker when you're doing this. Okay, so let's do this, do the selection. Okay, it's a bit of a faster transition, but the mesh is also just about as good. Keep in mind that if you're tracking relaxation polygons, you could include this area, and possibly it will benefit from relaxation. Sometimes it gets a little bit, yeah, see, it got a little bit bent out of shape there, but it's an option. Okay, that's the manual way of doing the same. Okay, the last thing I want to talk about is shore open water transition, shore to open water transitions. It's often the case that you're on the closer to the shore, or in this case, the inlet to Clifton Court. You're refining the flow field pretty small cell sizes or element sizes, but the open water you can tolerate something that's a little bit coarser. And you really have there's two ways that you can achieve this in SMS. The first one is what we call refinement nodes, which are a special kind of node that's placed in the map that can indicate a desired resolution. Second, the way you can do it is just put a smooth arc in that has your target resolution. So in terms of the quality of mesh that they produce, these refinement nodes tend to produce these kind of concentric circle artifacts. These generally can be relaxed away by using the mesh relaxation polygons. So usually there's something you can do about them. The arc method produces what I consider to be kind of a nicer starting mesh, but they both work. If just for completeness, the way that you do the refinement node in the map interface, you would choose to create the points using the create node button, and then you would select them, choose point attributes, and choose your desired resolution. If you're working with quads in an open water area, perhaps an open water area adjoined by a central channel that's higher res, you can use the stepping down of quads. So the vertex configuration for that is shown over here on the right. You've got a step down from a finer resolution quad mesh to a halved resolution quad mesh. When you generate the grid from that, it looks like this over here on the left, with this sort of interesting effect that I turned on paving over here and patching over here. Paving actually turns out to look more structured when you're doing this step down. My final remarks are reminders on a few of the numerical consequences of changing the grid and refining. Usually the incentive to do this is that you want to resolve some bathymetric or velocity gradients better. It's usually clear to people that when they do this, there may be a performance penalty. So certainly you're doing more spatial work, right? You've got more elements. You may also trigger a smaller subtime step in the transport part of the algorithm. The limiter on that is the element on the grid that is smallest relative to the velocity that is traveling through it. That can change through the tidal day, and that topic is covered elsewhere. A perhaps less appreciated consequence of refining is the effect that it has on the advection of momentum, or Eulerian Lagrangian / backtracking method that's inside of Schism. The error of that algorithm is proportional to the spatial step, or delta x squared, divided by the time step, or delta t. Refining in space will reduce error and sharpen tidal signals and other velocity signals. Refining in time, though, is in the denominator, so making it smaller actually has a sort of dissipative effect. And you can see that, but only if you grid over large areas, like all of Sassoon. So in our global case, which was the one that we opened this presentation with, that would be a pretty big deal. You'd see a big effect, and you might have to compensate with some of the parameterization. That's the end of this unit. I hope you've learned some things that you can apply to your gridding, and thanks for joining. Now, kind of a final topic, I want to talk a little bit about the consequences of refining. It's pretty obvious that you're going to track the bathymetry better, and you're going to be able to better resolve a sharply changing velocity field. But in addition, there is in the momentum advection part of the schism algorithm, there is an Eulerian Lagrangian backtracking that's used. It's to what they call the characteristic feat, and I encourage you to read the original schism and self papers to get a better idea of this. But this algorithm is one whose error is based on delta x squared over delta t. So you have this sort of interesting result that if you refine in space, you're going to be reducing error and generally also sharpening things like tidal range. Refining in time doesn't have the same effect. It actually kind of dissipates a little bit more and dulls the tidal range of a lot of quantities. These are considerations that matter if you refine over large areas like all of Sassoon Bay or the entire confluence region.